Imagine trying to understand a village water pump by only watching the handle move up and down. At first glance, it looks so simple, right? One action, one result. But the real story, the actual mechanics of drawing that water, is completely hidden inside. In this explainer, we're going to strip away the magic, drop the confusing buzzwords, and reveal the fascinating, hidden mechanism of quantum computing.
Think about the devices we use every single day. From the outside, quantum computing kind of just seems like another computer, maybe a bit shinier, a bit more complex, but under the hood, it operates on physical rules that literally do not match our everyday intuition. Ordinary computers, they're built to make very clear, definitive choices, 0 or 1, yes or no. But quantum computing completely steps outside of that binary world. And actually, that mismatch between what we expect and how it genuinely behaves, that's the whole point. It's exactly why the topic often sounds so mysterious before it sounds useful.
Okay, let's dive into part 1, the quantum difference. To truly grasp what's happening here, we have to keep one major anchor in mind. Quantum computing is absolutely not just faster computing. That's a huge misconception. It's a fundamentally different way of encoding and combining possibilities. Which naturally brings us to part 2, managing possibility. At its absolute most basic level, any computer, whether it's the smartphone in your pocket or a massive supercomputer, is simply a machine for controlling possibilities to get an output. Let's take a look at this comparison here, because it is absolutely foundational. Think of a classical bit like a light switch in your house. It's either exactly off or exactly on, right? Simplicity is its superpower. But a quantum bit, a qubit, is more like a spinning coin before it lands. It's not heads or tails yet in the usual sense. It carries this kind of unresolved possibility. It's genuinely described by a blended state. And quantum computing is entirely about managing that unresolved possibility, rather than just storing strict yes or no answers. And that brings us to the famous, or maybe infamous, concept of superposition. People often imagine a qubit is doing every possible calculation at once, just giving us all the answers for free. But actually, scratch that. That's not quite right. Imagine you're listening to two musicians playing a beautiful duet at the same time. The final sound you hear isn't just musician A or musician B. It's a uniquely combined result shaped by both of them. Superposition is exactly that, a controlled blend of possibilities. It means the machine can work with a structure of possibilities that our classical bits simply cannot represent in the same way. So how do we actually get an answer out of a spinning coin? Well, welcome to part 3, probability with design. We have to move from just holding those blended possibilities to forcing controlled interactions between them. And this brilliantly illustrates exactly how that works. Without this next step, superposition would just be a messy, chaotic collection of options. A quantum algorithm is basically doing two things. First, it spreads out across many possibilities. And second, it engineers interference. Think of it like acoustic engineering in a room full of echoes. If the room is designed just right, the sound waves from some directions get louder. They reinforce each other, while sound from other directions cancel out and completely disappears. Quantum algorithms do exactly this, but they shape the probability landscape. They create ripples where the useful paths strengthen and the useless ones simply cancel out. It's not just more probability. It is probability with design. Then we have entanglement. Oh boy, this one often gets a reputation for being pure science fiction. You might have heard it described as some spooky messaging faster than light. But for computing, entanglement is really just about shared structure. Think of two halves of a properly matched lock and key system. Knowing the shape of one half instantly changes what you can say about the other, because they belong to the exact same design. Entanglement lets a quantum computer represent complex shared relationships between many parts of a problem, seamlessly connecting them as a single system rather than isolated pieces. All right, now we enter part 4, the shape of advantage. Because eventually we need an actual answer, right? And this is where measurement comes in. Even after all those beautiful qubit interactions and acoustic engineering, a quantum computer doesn't just hand you a glowing list of every possible answer. You still have to measure the system. Measurement turns all of that engineered possibility, all those shaped probabilities, into one definite outcome. The whole job of the quantum algorithm was just to ensure that the one outcome you measure is highly likely to be the correct answer. Now, what's really interesting here is how this core mental model grounds everything we've talked about into one clean picture. Notice how classical computing builds answers through exact logic and sees one path at a time. Then look at quantum computing, building answers through probability and interference, literally shaping many possibilities at once. It proves that quantum isn't here to replace ordinary computing. It simply adds a completely new way for information to behave. So the absolutely crucial point here is this. Quantum advantage isn't magic. It's what we call representation alignment. Classical computers are excellent when the world can be broken down into clean, sharp decisions. But quantum computers excel when the machine's native rules align with the problem's native rules. When the problem itself acts like a network of linked possibilities, having a computer that natively speaks that exact language makes the computation incredibly efficient. It's a real game changer. That is exactly why quantum computing is uniquely suited for problems with a very specific shape. Simulating nature at the atomic level, like chemistry and materials science, is a perfect fit because nature itself is already quantum. Or take logistics. Imagine trying to move goods across cities with fuel costs, delivery windows, and road conditions all heavily interacting as a giant web of constraints. Because entanglement naturally stores those relationships, a quantum computer can hold the structure of these massive, interconnected problems much more naturally. But hey, we also have to ground the hype here. Quantum computers are not general miracle machines. I mean, you wouldn't use a highly specialized piece of equipment like a shovel to sew clothes, right? No way. In the exact same way, a quantum computer is terrible for ordinary web browsing, writing documents, or simple arithmetic. For problems with little exploitable structure, classical computers and our everyday laptops are not just sufficient, they are absolutely the correct and superior tool for the job, hands down. Let's move to our final section, Part 5, Expanding Reality, and see how this builds a completely new mental model for us going forward. We've gone from just looking at the handle of the water pump to finally understanding the gears inside. You now think like someone who sees computation as a physical system, an environment shaped by the laws of physics, rather than just a pile of software code. You know that a quantum computer uses uncertainty strategically to compress useful structure into a final measurement. And that is where real confidence begins. Quantum computing is no longer a mystery box. It's a highly specialized way of guiding information through possibility. So the next time you see a headline making wild claims about a new quantum breakthrough or some massive speedup, you don't have to wonder if it's magic. You have the ultimate tool to cut through the hype. You just have to ask yourself, what kind of problem has the right structure for quantum rules to actually help? Keep asking that, and you'll always understand the real story.